Log on, tune in, find out. Another good idea from Cambridge.
We've got two 30-minute talks this afternoon, both by PhD students at the University of Missouri. I'm very glad that they were able to join us in this program because the normal funds don't give us anything for PhD students at all, and so other pockets have had to be raided. We're going to start off with Adam Lane telling us about information in a two-stage adaptive design. Adam, over to you.
Can everyone hear me? All right, is the microphone picking up? I guess so. All right, so my talk's going to be on information in a two-stage adaptive design. The original problem was motivated by Val Fedorov, and then I've been working on it for a few months with my advisor, Dr. Flournoy. And then she had a previous student, Ping Yao, who did some work while he was still at the University of Missouri. So first, the motivation. Does considering the dependence of stages in a sequential design affect information? And of course, if the stages are dependent, you would expect that the information would reflect that. So the first step might be to find that effect analytically, and then more important to us is the question of practically. So if you have two stages, two dependent stages, and you find the information accounting for dependence, do you really see a big benefit practically over if you just took the assumption of independence and used that information measure? Okay? And so we're going to look at that from two different perspectives. First, or try to address it from two different perspectives. First, from a design perspective, can an information measure be used to make design parameter decisions? And second, from an analysis perspective, is there an advantage to considering the dependent information measure in place of the independent measure as an estimate of variance? All right, so first I want to motivate the problem in general. So we have Ni subjects are treated at Xi with weights Wi at each stage. And so we have two stages, and we'll have responses Yij equal to some mean function plus a normal error term. And then the function eta it depends on your treatment level and a single one-dimensional parameter theta. And so we're thinking in most cases we're wanting to think about eta being a nonlinear function. But for our example, the linear case actually, when you take into the adaptive step, the linear case actually is quite interesting as well, but we haven't considered it really. So whether or not you actually have dependence of stages, your likelihood is as follows. All right. And I don't have anything on this in my presentation, but in Nancy gave a very similar talk earlier in this here at the Institute. She gave a couple of slides on how this actually works out. So reference hers if you're interested. So here's our adaptive procedure. So we have a score function. Once again, the likelihood doesn't matter about whether or not it's dependent in terms of the form. So your score functions won't matter in terms of form of whether or not you have dependence or independence. So the adaptive procedure here is to select a second stage treatment by finding the argument that maximizes the variance of the second stage score function. And then evaluate it, so it's evaluated at theta hat 1, which is the MLE of the first stage data. And so x2 is an estimate of a locally optimal design point, x star, which is if you were to maximize the variance as a function of theta. So x star is a function of theta. And so you can see how this will cause problems because you have to have x2 has to make sense from a design perspective, right? Because if you have 0 or infinity or anything that doesn't depend on theta, then x2 has no meaning for your particular problem. So this is where some of the problems come in finding this value of x2. And then of course, if the MLE is consistent, then then x2 will be consistent for x star. Okay, so to derive the information, we consider this total score function, which is just a sum of the two-stage score functions. And then you have an expected information. So here we're going to denote the true information measure as m underscore DEP, so to indicate that we've accounted for the dependence of on the stages. And so that's just equal to the variance of the score function divided by the total sample size. The only thing that should be somewhat or not completely obvious is maybe that the covariance is equal to 0. But if you look at it, if you write everything down and you look at it in terms of successive conditioning, taking expected values with the successive conditioning, it becomes fairly obvious that it is the case that the covariance will equal 0. So you're left with this as your information measure. And so you can see that it is a function of your first stage data. So you just take the only thing that's really interesting here is you take the expected value over it. And so so the other measure is if you take x1 and x2 to be considered fixed, so you're approximating your dependent measure by using an independent measure, which you just get rid of the expectation and plug it in, right? So it's just a question of whether or not averaging really has a big impact in this sense. All right. So, and one interesting thing is that for a specific function eta, these two may not actually have the same asymptotic limit. So I haven't really done much with that right now, but it's a comment that something that I've noticed, but that I'd like to research at some point, but haven't had a chance to. Okay. So for our particular example, we took eta to be just a one-parameter exponential mean function. So we've only considered theta here to be on the positive real line, and then the practical consideration is that you have to consider you're going to fix some design interval in practice. And so the idea here is that since you have to fix an interval for your design, then it makes sense to try and maybe restrict your interval for theta in terms of your MLE. And you kind of have to do this, if I can just put up real quick, because you maybe remember, if you've ever seen, that the mean function that we have is bounded between 0 and 1. And so our likelihood function, that goes through 0, can only be maximized if your mean is if your y bar 1 is between 0 and 1, right? So you have to restrict the only problem. So you could let this be 0, but you have to restrict this because you can't have infinity here. But if you let this be 0, then your treatment level is now infinity, which doesn't make any sense. So you have natural restrictions that you have that come out of the design of the problem. So this does cause some significant problems, the boundary issues, because we have we're essentially using a model with it's a good word. It has deficiencies in our model. We have a mean parameter, or a mean that is restricted 0, 1, but a response that's negative infinity to infinity. So we have a problem with when y bar 1. So if you think of an illustration, when theta is equal to 1, n is 100, x1 is 2, and you have boundary values of 0.1 and 4, then the probability that theta hat 1 is on a boundary, if w1 is equal to 2, is for the case where it's at 4, it's 27%, and then of course when it's this, it's negligible. But this does cause problems, and the first place you can see it is in the plot of y bar 1 and y bar 2. So here at 0, you know that your likelihood isn't going to be well defined, or your score function is going to be increasing. And so you have a whole bunch of cases where you're at a boundary value, and so this affects y bar 2 in the sense that now you have two conditional distributions, or at least that's how I've plotted it. You obviously have a mixture distribution, but it's a mixture distribution that's of two combined conditional distributions. So the light cases are where y bar 1 is less or is greater than 0, and the dark cases are where y bar 1 is less than 0. All right? But so it has a pretty large impact in terms of these histograms, but when you go to actually do your estimate, once again here we're considering conditional distributions, you can see that you're actually not doing too bad. So the true parameter is 1. So the light cases, which once again is when y bar 1 is greater than 0, is slightly biased, slightly negatively biased, and then the dark cases where y bar 1 is greater than 1, or greater than 0, are slightly positively biased. So overall, it's doing a pretty good job at estimating the true parameter in both cases. So just as a quick, to summarize the bias, so this line is the bias, the true bias of if you just were to do a single stage at x1 for all 100 samples. The second one is if you are to do it's the bias of this from simulation, the mean of the simulated biases from of theta hat from as a function of W1, your first stage sample proportion. So you can see it's an increasing function. So the less you put at stage 1, the less bias you're going to have. But of course, variance is a whole other matter. All right, so here back to information. So on the left, we have the theoretical measure, we have the true measure of information. So it's constant with respect to theta hat 1, but the idea here is that the independent measure has a lot of variation in terms of theta hat 1. So these plots are just taken at W1 of values 0.25, 0.5, and 0.75. So the point here is that from a design perspective, MIND is only going to have use if W1 is very close to 1, in which case they're the same. Because it depends too much upon your first stage value. But the dependent measure is constant, so you actually could maybe do something in terms of picking a design parameter with it. All right, so to kind of motivate further the idea of the dependent measure, you can use the Rao-Kramer lower bound, which everyone's probably familiar with. It just says that there's a relationship between any estimator and the inverse of the information. So we're hoping that there's maybe to motivate that you can use the dependent measure in place of the inverse of the variance. Okay, so one way you might try to use that is to try and find out some sort of optimal value for W1. And it's going to be noticeably it's just a practical it's not a theoretical thing, but it's just a way in which you might be able to use this. So you have the let W1 star be the argument that maximizes your information measure with respect to W1, and then do that. So you've already restricted your interval theta. You've restricted an interval between here. We've done 0.1 and 4. So the idea is just run this procedure for each value of theta across this line. And so you can see that, of course, when x1 is equal to 1, the locally optimal that is locally optimal when theta is equal to 1. So you're never going to be able to beat that. But as you come away from that, it drops off pretty severely and kind of levels out at some point. Of course, it will eventually go to 0, but it levels out in some sense. And so you could take a weighted average of some type of this line to help you understand what could be a good value for W1. So now on to estimation. So we're considering the two measures of information, except now we're just going to, in terms of estimation, you just evaluate it at your theta hat. So once again, you can see the difference here. You're just plugging in your value, whereas in this case, you take the expectation, which we have these boundary values. So the pi 1 and pi 1 hat and pi 2 hat, or pi 3 hat are just the same, the probability of your boundary values mentioned earlier. And then you take the expectation, but with respect to, you're evaluating the expectation numerically at theta hat. And so in this plot, we try and get an idea for how much is actually being accomplished by considering the dependent measure versus the independent measure. So the black line is the simulated variance, the variance of the simulations, the inverse of the variance of the simulations, compared to the quartiles of each of these estimates. So you have to look pretty long and hard to see much of a difference at all. So it is a little tighter, for the dependent measure is a little tighter in distribution once you get past maybe 0.05, and then that tightness decreases as it moves up W1. Right? So the real thing to see here is that there's not a very large difference between the two. Then compare, so this is kind of comparing what you're doing to, what we call the locally optimal case. So locally optimal case is where you take x1 is equal to the same x1 as it would be in the normal case, but then x2 is equal to the inverse, it's equal to x star. So in this case, that's the inverse of theta. So it's the best you can do with an adaptive procedure, given that you started at x1. So it's kind of trying to show you how much you lose theoretically by considering the information measure, the adaptive information measure that we're using, and then how much, again, is lost when you actually do the procedure in terms of the variance. Okay. There was one thing I did notice in terms of to show that MDEP is actually doing a little bit better as an estimator is to compare how many cases how often is it closer as a percentage. And so you can see once you move past 0.1, it's always closer to the inverse of the simulated variance. But once again, the magnitude of those differences is not that great. Coverage, so this is just each coverage of each, so it's the number of simulations divided by the total number of iterations. How many times if you were to use theta plus 2 times the inverse of, or the square root of the inverse of that measure, does it include your actual value? And what's surprising here is it's doing a fairly good job once it gets past 0.1, which is surprising considering when you look at the actual estimates, it seems like they're doing pretty poorly in terms of estimating variance. So I haven't actually figured out what's going on here and why it seems like we're doing quite well in terms of coverage when it seems like we're doing so poorly in terms of estimation. Maybe somebody has a better idea of why this could happen, but yet, as of yet, I haven't actually been able to think of anything. So conclusions, there is a potential use for the dependent measure from a design perspective. But from an analysis perspective, there doesn't seem to be too big of a difference. So if what you're interested in is analysis, then for this specific function, you should be able to just think of using the independent case and you'll be all right. Future work. Now, this first one I find particularly interesting for our specific problem is that there should exist a case where the dependent and independent measures have different asymptotic limits. So in this situation, will this have a greater effect on the dependent and independent measure when you go to do analysis? You would think it would. So the basic thing here is it might not even need this criteria. If you pick the probit or the logit or some other function, does that have a bigger effect on your analysis in terms of estimation? And then to extend, of course, another extension is to go to a multiple dimensional parameter space. And then something I've did a little bit of work on already is, we considered in this example, WI was fixed. But you might want to think of a very, very small first sample size and then an order of magnitude larger second sample size. So if that's the case, then you might want to look at it as fixed. All right. So are there any questions? Sorry.
Any questions? Okay, I have a question.
All right.
You were talking about what happens asymptotically. I've never dealt with an experiment where the numbers were anything like where asymptotic theory would come into play.
You mean?
I mean, in practical experiments,
Right.
are the numbers going to be large enough for asymptotics to be relevant?
Well, yeah. I see. I mentioned that the two may have a different. May have a different asymptotic limit, and that. But my point is that if you know they have a different asymptotic limit, it might indicate that in the smaller samples, you may have more of a difference in terms of estimation. That's what I meant. I mean, it's not that you're going to just consider the asymptotic. It just may indicate that there's a bigger difference in terms of estimation. Yeah. Yep.
Adam, this is an interesting problem because in practice, most people first perform a pilot study before they perform the real study. And
Right.
That's actually what you are doing. But I was wondering, you were talking about extensions to other sets of parameters, more than one parameter. What kind
Right.
of models are you thinking of?
Well, you could just use a two-parameter logistic, or you could use an exponential, but have it be both have a scale and a location. So there's a location exponential distribution, if you wanted. Because the nice thing about the exponential distribution is that you can actually work out some of these things analytically, whereas with a probit, you have no chance of finding x2 analytically. So that's why we picked this particular example. But yeah.
So that will also be part of your thesis?
Well, it depends on how far I get on the first stage sample fix. I was actually working on that problem first, so depends on where I get with that, I guess. But at some point, I'd like to do multiple dimensional parameter space. Yep.
I have some comment. Can you go to the slide where you find out some optimal W?
Yes.
You didn't number them, at least I have not seen numbers. And I think it's not very actually good, very good method to define optimal partitioning. See, the matter is that your information matrix or information here is random variable, and distribution of random variable is very skewed. And so I do not understand why you say maximum. So it's
Well, in this case, this is not a random
it
variable,
mean
though.
or what?
Well, this isn't a random variable. This is fixed for theta. So you're thinking about maybe the estimator, but this
Or
is
you have theta here fixed, so some kind of local selection.
yeah, it's a local selection method. So here's your local. Everything is so it's doing this for each value across this line.
So probably what you have to do, maybe you can do it analytically, but at least I know that people do it in simulation. You actually take into account that n is actually random, because it depends upon, you do not know theta, you know estimator of this theta. And then you try to maximize some quantile of this distribution, because mean can go very nicely and for very small W, for very small sample sizes for the first stage.
Right.
But variability
Yeah.
in your information will be so huge, so it will be useless to have this small sample size for stage one. Therefore, it's reasonable to look at some quantiles. For
Right.
instance, that in 95% you are better off with this W than in
Yeah.
only taken into account mean, or at least take median.
Yeah. I get what you're saying now. Yeah.
I
see.
think, your original motivation for creating this picture was not to find an optimal W. That sort of came later.
Yeah.
You didn't really talk about what this was telling.
Well, originally I did just to find out. I mean, it's just kind of to see what you're doing, but the same thing would apply. To, the original
The
problem
point you
would have still.
didn't make is that what this shows is, the optimal, that if you were so lucky as to pick your first design
Yeah.
point at the optimal level, then there's a region where not adapting is better.
Right.
That's where W1 equals 1. So if you were so lucky as to pick your X1 in that region, then forget, then
Right.
you're going to be worse off by adapting. And the point then is to say, or the consideration is that the width of that interval is really small. So the chances, if you're kind of, you have to have some probability distribution on,
Right,
how you're gonna
right. But
pick
his point would still apply in that case, I think,
The
because
problem is that you
his
do not
his
know
his
that
point
you
still
are
applies.
Good region. You do
Right.
not know parameter. You know estimate.
Right. That's his point.
So at
Still
the
would-
beginning, you don't know any
Yeah.
of the estimator.
Right.
Yeah, but even in the middle, if you
Yeah.
interim look, so
Okay.
I get your point. I don't have I can't
Okay.
respond to it right
It-
now.
it
but
looks
yes, I get
like-
your point.
you got it.
Yeah. So, are there any other questions?
What about 3 stages or more?
Okay. Yeah. Someday maybe.
She's
I mean,
already
it's true
thinking
that
about
as soon
5
as
stages.
as soon as you get a lot of stages, then you can invoke martingale theory and a lot of things.
Right. So,
A lot of asymptotics work out, how things
but
work
it's
out
like
exactly.
Martin said. I think most people want to do a small, like what do you call
Pilot
it?
study.
Yeah, pilot study and then a big study. So that's aimed at this. So you could do 2 pilot studies and a big study, but I think you might want to do when people extend to multiple stages, you might want to do infinite stages or a huge number of stages to use the theory there.
But this dependence would somehow accumulate.
Yeah, I mean, like she said, use martingale theory in that case.
And FDA says it should be 3 stages. Phase 1, phase 2, and phase 3.
But a lot more changes between the stages than
Yeah.
just this.
Well, Adam, thank you very
All right,
much
thank you.
again for that.